Well, my watch tells me it's 8:30. Good morning. Let's begin. Any questions about anything? So we talk about forces, and in general, we will analyze, study, two different important situations. One we call equilibrium, when a system or an object is at rest and net force equals to 0. And second, when net force is not equal to 0. And yesterday we saw some experiments which allows us to make a connection between mass of a system, net force acting on it, and the acceleration. So there's one more. I'd like to show, how do I do that? This is how. So that's not new. We saw it yesterday. A force propels this cart. We can manage masses, measure acceleration. But what's going to happen if I add a sail or a wall to it attached to the cart? Oops. Nothing. Take it out. It starts moving. If the same sail is not attached to the cart, moving, what does it tell us? Well, this demonstration has 2 points. Number one, it supports the Newton's third law, because forces which act on the wall and back from the wall must have the same magnitude. Otherwise, one force would be stronger than another, and the cart would have been starting moving in one direction or another. And second, even more important fact for the future, these are all parts which belong to the same system. And what we observe is interaction inside the system. That's what we call internal forces. We can see internal forces don't affect the motion, the state of a system as a whole. I can give it a slight push, and it will be traveling, keeping the same velocity. But as long, as soon as I take it out, that's it. The same force becomes external relative to the system, starts pushing, and we observe acceleration. Switching back to slides. And Sir Isaac Newton didn't have this type of equipment, of course, but he was a genius, so that's why he was able to establish a mathematical relationship between these three physical quantities: acceleration, mass, and the most important part of it, net force. Net, which by definition is a vectorial sum of all individual forces acting on the system. And the nature of these forces don't matter. Could have been any possible forces. Still, the first step always finding, calculating, drawing, looking at the net force, and then see how they related to each other. But, so this is more or less how Newton wrote this law. Acceleration is equal to net force over mass, but we people hate fractions, so this is how normally every textbook offers the same law. Mathematically, absolutely identical, but no fraction bars. And I personally don't use that symbol, sigma, very often. I just show explicitly that's the net force. Net, not just any, not the first, not the last, total. Now, there are two types of non-equilibrium. This is what we just saw. When acceleration is not zero, acceleration is not zero, the object speeding up or slowing down, for that matter. And sometimes net force is zero, but the object is still moving. Well, in that situation, the velocity must remain constant. If acceleration is zero, that means object has no acceleration, travels at constant velocity straight ahead with the same speed. So theoretically forever until something stops it or changes its motion. Well, if I have this cart and I slide it, it stops because of the friction. But we can imagine that friction has been removed. Well, we could put some ice, oil, wheels, friction would be practically eliminated. In that case, the same object would have been traveling, well, theoretically infinitely far away until some other object would start acting on it. So that's what was a genius of Newton, because before him, after Aristotle, everybody thought that force and velocity are related directly. But no, he established that force and acceleration are related. Velocity doesn't need any support. If you in the outer space and throw an apple, that apple will fly away from you forever until it hits Alpha Centauri. When velocity changes, that automatically means acceleration is not zero. When acceleration is not zero, that automatically means net force is not zero. So that must be at least one force acting on that object when velocity of an object changes. So technically, that completes all theory. We have a choice. Go home or practice. What do you choose? Practice. That's her fault. So, first, of course, we start from simpler situation, static equilibrium. Static equilibrium happens when system is at rest. This word rest might be tricky. Theoretically, it means velocity equals zero, all right? But we know that if I have a ball, toss it up, at the highest point of its trajectory, velocity becomes zero. Does it mean it's equilibrium? No. The key word is remains. It has to remain zero for a long time. Velocity remains zero for a long time. In that case, that's equilibrium. Like this. Oops. All right, I'm going to do it again. I'm going to show you and block you simultaneously. I'm not sure if camera will help, but we never know. What do you see here is equilibrium. Actually, two objects are in equilibrium. This weight is in equilibrium, and this little nut is in equilibrium. So this weight has only, how many forces acting on this weight? Two. Force of gravity, because it always acts on everything. plus we can see there is a string. Force of gravity pulls down, string pulls up. They must cancel each other. So the force inside this string must have the same magnitude as the force of gravity acting on this weight. That's 1 kilogram weight. So mg means 1 times 9.8. Force of gravity of 9.8 newtons acting down. And in this string, 9.8 newtons pulls it up. But the same force in the same string will be acting on this little nut down. And we can see 2 more forces. And we can read the numbers. 8 newtons. 4 newtons. What else can we do? Well, now we can use a protractor and measure angles. So it looks like 60. I need a level, and I don't have it. 55 or so. All right, on this side, this is a very simple experiment, doesn't have to be absolutely accurate, so let's say 70. So now I have to use my short memory, 55, 70, okay. That's all we need. Now we have to use this information to, well, first we want to prove the fact that net force is indeed equal to 0. That's a mathematical exercise on geometry. Technically, again, because it's physics class, we shouldn't be doing that, but we will. At some point, I will ask you some questions. I don't know what questions I will ask you. I only know I will. So first, of course, we have to copy. So you have to draw your picture. I have to draw my picture, which represents the experiment. Something like that. Now, of course, here, nothing interesting is happening. Very simple. This is a force of tension. This is a force of gravity acting on this weight. They must be equal to each other in magnitude. So that gives us 1 times 9.8, 9.8 newtons. Now, this is the picture. I don't really need the whole picture. I only need the diagram. So all I need is just a diagram for forces acting on that little nut in the middle here. So there's a force acting this way, and it's strong, 8 newtons. There's a force acting this way, not as strong, 4 newtons. There's a force acting down, the strongest one, 9.8 newtons. And we have measured angles. I'll call them alpha, beta. Alpha equals 55 degrees, beta equals 70 degrees, plus or minus 10%, because it was really, really difficult to measure the exact angle in these conditions. So, of course, our final result also will be plus or minus 10, 15%, which is fine, especially for labs. So what do we do? Well, since we know angles and forces, we can calculate net force. That's our goal. And to do that, first we have to label all 3 forces. Let's call them 1, 2, 3. The net force has to be equal to first plus second plus third. This is the vectorial expression, but we know now that we can break down every vector into components and analyze all components individually. So the same equation can be written for x component. And basically, when we make a transition from vectors to their components, all we have to do, replace an arrow on the top with a letter at the bottom. That's what we need to calculate. And of course, the same expression for the y component. All right. Now comes my question. F pre x. A component is a number. As any number, real number, and only real numbers we use in this course. As any number, that number might be positive, equal to 0, or negative. There are no other options. So these are your choices for question number 2. What do you think about the x component of the third force? The third force is much more important than the first and the second. Yeah. Republicans, Democrats. The third force. You. So, please enter your answer. I'm going to check the web sign. "84 out of 92. Number 2 is winning, and number 2 is correct. Third force is vertical, so it has no horizontal component. That's it. We've had a similar situation before discussed when we talked about free fall acceleration. It points straight down. Yeah. So we just called it negative g. It does have vertical component because it's vertical, but it has no horizontal component. That makes this force special because it makes calculations easier. Well, anyway, what do we do now? Well, now we just continue calculating the x and y components of the net force. F1x. This should have been my question. That's the force number 1. Please tell me the x component of the first force, positive, 0, or negative. As long as you want to say it, say it. I just didn't hear. Please say again. Negative. Yeah, we have to do it automatically already. We shouldn't be spending time on that. The component points opposite to, well, first of all, of course, we should draw it. This is F1x. It points opposite to x direction, so it's negative component. What should be the value of this component? Hypotenuse times cosine of alpha, which is 55. And again, this part should be done automatically. It's a right angle triangle relationship applied to this particular physical situation, nothing else. Now, F2 plus F2 x. That's this. It's positive, and it should be equal to hypotenuse, which is 8, times cosine of that angle, which is 70, and plus 0, because the third force has no x component. And now we need to write a similar expression for the y component of the net force. Net force. So Make it. Bless you. Yeah. This is the y component of the force number 1. This is the y component of the force number 2. And again, y component is positive in both situations here and opposite to the angle, so we have to use sine. So 4 times sine of 55 plus 8 times sine of 70, and plus, because we are adding components, see, this plus comes from this plus, and this plus comes from that plus. So, but what number should I write for the y component of the third force? Negative 9.8. Now we have to take a calculator. Please take a minute and calculate and tell me the values. F net x equals F net y equals. And for that, you don't need the screen. So I'm going to switch. By now you should have all the information in your notes. Too slow. So this thing. So what do we get for x component of the net force? Let's compare our numbers. Anybody? What's your number? What's your number? Well, we can round it up. 0.4 newtons. And for the y component, and again, this is a case when you shouldn't spend too much time on a calculation like that. It should be you should be familiar with how your calculator works, so you would just press the buttons, done. 4 times sine 55 plus 8 times sine 70. Oops, my calculator needs light. Minus 9.8. So it dies without light. So what do we have for y component? About 1, yeah. This is not very accurate, of course. It looks like it's far away from a 0, but if you compare with magnitudes of forces, that's actually not so bad. If you calculate the percentage error, like difference between the forces, 10 and 1, 10%, which is, again, for this experiment, pretty good. So this type of experiment has been used to prove that if we make it more and more accurate, net force will be more and more closer to 0. So in equilibrium, net force is indeed equal to 0. Now, we can use this fact backwards to answer some questions. Well, this is a very common experiment or demonstration, you have 3 different weights. Here I have 50, 50 plus 20, 70, and 100. And, well, what's going to happen if I have only one weight attached and I let it go? That's not equilibrium. Yeah, everything's moving. So question basically, how can I make it in equilibrium? Well, I have 2 additional weights. I can attach those weights. Not so easy. You're not going to run away. Where's my... Number 1. I left my 3rd hand at home today. That's 50. That's 70. Well, so we can find the equilibrium easier in this situation just by finding the right, well, not right, correct angles by shifting, okay. And to see when the ring practically is in the middle, and then we can measure these angles, and that's it. So from 0 to 150, 150, from 0 to 70, 70. The question is, of course, how could we calculate these angles mathematically and then assemble the system and see that it actually works? Turns out calculating those angles is much harder than the algebra we know. In reality, I'm going to this is what we should do. So again, we should start from drawing a diagram. We still have 3 forces. Well, in this situation, they're acting on that little ring in the middle. And each force equals mg, mg, mg. G is the same for all. So we can measure forces in grams, not in newtons. So one force equals 100 grams. Second force equals 70 grams. Third force equals 50 grams. The angles we are looking for, well, technically these angles, all 3 of them. How would we do it mathematically? Well, again, we can draw x and y axes. And we can say, okay, these are angles we're looking for, because if we calculate these angles, we can find all other angles. Now, we know that according to Newton, the god of physics, net force acting on that ring has to be equal to 0. And we know, because we have it proved, so, and we know that it means relative to x-axis. Again, column 1, 2, and 3. Relative to x-axis, force number 1 has a negative component. F1 times cosine alpha has to be negative. Plus, force number 2 has a positive component. Actually, I know the number, 100 grams. So force number 2 has a positive component, 70 times cosine beta, plus force number 3 has no x component, and that has to be equal to 0. We're done with the x component. For the y component, force number 1 has a positive component. Same equations we just wrote 2 minutes ago, just different numbers. Sine of alpha plus force number 2 has a positive component. Sine of beta minus 50 equals 0. Again, I use grams for forces. Why not? I can convert grams into newtons if I want to, but that conversion factor would have been canceled anyway because everything is equal to 0. It would be a common factor. And these are equations we have to solve for our unknowns, alpha and beta. There is a way to do that, of course, algebraically, because, well, you have to use trigonometry. Cosine and sine are related. But that would have been too much work. So what do we do instead? We use achievements provided by, well, in this situation, Wolfram Alpha website. Wolfram is a name of a person who created Mathematica as a software. I met him. He's very smart. And they're actually based here in Massachusetts. So they have a lot of resources people can use to run lots of complicated calculations, which wasn't possible like 10 years ago, 20 years ago. So we can go to graphs, and we want to solve equations. So we go to equation, and we click on any equation, and we have to check if it works. Works. Because not every browser actually, by some reason, supports it, but you can always find another browser. Well, so see, there is an equation, and we can see the graph of that function right here. Our equation, of course, is different, so we have to erase this equation, and we have to enter our first equation. So negative 100 times cosine, well, A, letters don't matter, plus 70 times cosine B equals 0. Let's see if this works. Oop, I made a typo. I have to erase a D. All right, once more. Okay. Now, we need a second equation, so we just have to plot it. Plot means type in plot. Now, let's see. Let's hope, fingers crossed, 100 times sine A plus 70 times sine B minus 50 equals 0. The crucial moment. Yeah, you can see two graphs, but you also can see that those graphs somewhere cross each other. So this point represents solution for both simultaneously. And this. So what you can do, just hover the cursor above. Where's my cursor? And read the numbers. In this situation, what I read is 0.86 and negative 0.38. Well, I don't like negatives. You know that in trigonometry, any equation which has sine or cosine technically has infinite number of answers. So they don't matter. You can choose any number, but what you have to remember, these numbers are radians. because technically radians is a standard unit for angles in an international system of units. So if you see 2.2 or 2.7, those are not angles, those are radians. If you need angles, you have to use a convergent factor. Pi radians equals 180 degrees. And that's it. So this is a really, really powerful tool. And in a lab, you will be forced to use it because we talk about forces. Any questions? Well, every time when we have to solve a problem like that, we have to choose x and y axes. And how can we select those x and y axes? If you want to answer the question, how can we do that? What would you say? What would you say? Yeah? Yeah? Exactly, right. We can choose the axis any way we like because nature doesn't have axes. It's for us. It's in our mind, just to make a description of the nature easier for us. So every time we can use that flexibility if we want to. This is, again, one more problem. And first, you should draw a free body diagram and answer the question, how many forces are acting on this person, on this lady, or from our point of view, just an object? Your diagram has to show all those forces. Because if you miss a force, you miss a component, and then your equation will be wrong in the end, and you don't want that. So by the way, it was assumed, but now probably I should say it out loud. Communication is encouraged. If you talk to each other, that helps. Both or three of you who talks. So if you have a question, feel free to discuss it. Question? Okay. In the previous?
Yeah, have you found the numbers for the net force for the x and y component?
This or previous?
So we found the forces for the x and y components.
I don't understand the question. First of all, are you talking about the knot with the scales or the force table with weights?
With the scales.
All right.
So you know how we found that x component in that force, and we found the y component within that force?
Yes.
So,
And we said after that even these numbers not really equal to zero, they're small enough to convince us. So if we would make this experiment as accurate as possible, these numbers would have been almost equal to zero. That's the point of this. That's it.
okay, so we don't find a combined net force, it's just the net force of the separate components?
Well, if the x component is zero and if the y component is zero, the whole force is zero.
Okay, so that was the point of that, the x and y components should be zero, so
Yes? Thanks. All right, so please, if you think only one force acting on that lady, raise your hand. If you think two forces, please raise your hand. Three forces. Okay, we're done, practically. We just have to list the forces, draw the diagram. What is the third force? Gravity. Yeah. So, one more force. mg. But of course, we need a diagram. So, we represent this person as a dot. In physics, everything is just a dot. Force. At 31 degrees to the vertical direction. This force at 15 degrees to the horizontal direction. And the force of gravity is always vertical, and that's going to be equal to (550 newtons). So in this situation, we know angles and one force, so we're able to calculate other forces. And in this situation, again, the strategy is exactly the same. Yes? There is normal force. You are a little bit ahead, but that's actually a good question. But it's a question about a definition. So if we have two objects touching, like a wall, that doesn't matter. And something else also doesn't matter. In general, this force, the force of the contact, might have any possible direction. But as any vector, it always has components. We always can resolve this force into two components. One will be perpendicular to the surface, and second will be parallel to the surface. Now, these components historically are treated as individual forces. This, what we call the normal force, and this, what is a friction. So in our situation, the red arrow represents the contact force, which is a combination of two forces. Theoretically, there is normal force like that and frictional force like that. You just ignore these details. They're not important in this problem. Now, the strategy says we have to add what? What's missing in this picture? X and Y. Actually, so if it's missing, what do? We add them to the picture, we draw them. Yeah, it's always a standard action. There is something which we need, and it's not there, so we add. That's it. Nothing special. So, well, in this situation, natural choice, again, for the axis is horizontal and vertical. And we write the same equations the third time. Yeah? We just don't call forces 1 and 2. We call them T and F. But how do we call them? Doesn't matter mathematically. Relative to x-axis, what matters is angles. This will be Tx, and this will be Ty. This will be Fx. This will be Fy. And the relative to x-axis. Well, okay, let's write it first explicitly. Tx plus Fx plus mgx has to be equal to 0. And Tx is negative. And to calculate it, we have to use the hypotenuse, which is the magnitude of that force. And we have to multiply by the corresponding function relative to this angle. The angle alpha is opposite to the component. So what function should we use if we use that angle? Sine. So the function depends on the actual triangle and actual angles given to us. Sine of 31. Plus, second component is positive equals magnitude, which is hypotenuse, times cosine of 15. And the plus 0 because weight has no component relative to x-axis equals 0. Now, second equation, y component, tension times cosine 31 plus whatever contact force times sine 15 minus 550 equals 0. Now these equations are much simpler than we had to solve using Mathematica, because these equations not about angles. We know angles. These equations about standard variables, t and f. And so the approach is standard. For example, first we can solve the first equation for t. Doesn't matter what. So because I don't have much space, I do some work in my head. And because I do that, I might make a mistake. So you have to check what I'm doing. So it should be equal to f cosine 15 over sine 31. Of course, you can take calculator, calculate these cosine, sine, doesn't matter. Now what can I do? Now I can use this expression here, plug it in to replace the unknown with a complicated expression. But if we do that, the result will have only one unknown left in that equation. So I'm replacing the whole thing. So 15 sine 31. I keep cosine 31 because it was there initially, plus f times sine 15. And that all has to be equal to 550, because I just move it over there. And now I can solve this equation for force. So what can I do? I can solve it because this variable f is a common factor. Pull it out, parentheses, and do mathematics. 550 divided by what's going to be in the denominator, cosine 15 over sine 31 times cosine 31 plus sine 15, blah, 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 blah. Again, that's mathematics. And now you have clear example of how that mathematics works. At this point, all you have to do is just finish calculating that force. And when you know this number, you can use it back here to calculate that number. Done. Any questions? You have a practically same problem at home to do, so practice. Yes?
So can you also use the for the t side?
That's a good question, so I'm going to ask you that question. I prefer when people sometimes answer their own questions. So if you have a triangle, and in this triangle, you know this angle, A, B, T. Do you have to use 31 degrees? No. So it's your choice. Since you know geometry, you know this angle has to be equal to what? Y? Because these angles, well, three angles together should be equal to 180. In a right triangle, two angles together should be equal to 90. So it's a matter of your personal preference, basically. All right. So when an object is not in equilibrium, we have to apply Newton's law, naturally. That's the first situation when everything is in the same direction. Again, we start from a diagram. An object, a car, is being pulled, so we have two forces acting to the right. There is general force of resistance. Technically, we should add two other forces because gravity doesn't disappear anywhere. Normal force doesn't disappear. However, these forces cancel each other out. We know from our common sense and everyday experience, in this situation, velocity should point to the right, acceleration should point to the right. So theoretically, we could use both components, but only x component gives some meaningful result. Relative to y component, everything cancels. So relative to the x component, what can we write is, well, you see the numbers. 275 newtons, force number 1. We have to add 395. We have to subtract 560 because it points in opposite direction. And that should be equal to mass times, well, technically, the x component of the acceleration. So, well, we know the mass. It's in tons, but 1 ton, 1 metric ton equals 1,000 kilograms times a. So now we just have to solve it for acceleration. I think I have a slide. Yeah, that's it. This is a simple illustration, but it includes all important steps of the strategy for any problem related to forces, mass, acceleration, to Newton's second law. Diagram, forces, in general, both axes, equations. This is a specific representation of the Newton's second law of mechanics. That's a general equation. This is specific, applied to this specific car, specific object, relative to specific axis. Well, next case. In this situation, we have two objects. So we need to draw a free body diagram for each. When we do it for the first, we can just forget about the existence of the second and vice versa. So we can close our eyes or, imagine, cover this and draw a diagram for that, cover that and draw a diagram for this one. The object on the left, the object on the right. So that's what you should do right now. I'm just giving you time, a head start. You should draw two free body diagrams. First diagram for a 3-kilogram box sitting on a table. Second diagram for a small object attached to a string. This is basically something like this. Well, actually, right now there's a 50-gram weight attached to it, to this string. And what's happening? Nothing. The system is in equilibrium. Both objects are in equilibrium. Why? What force prevents it from sliding? Friction. So we have two options to make it move. We can oil it up, or we can attach a heavier weight and see what's going to happen. Oops. That's it. We're going to talk about friction after the first exam, but you can see that friction plays a very important role. Oh, I broke it. And this experiment actually tells us how can we measure friction. There is critical weight, which we attach and starts moving. Well, so how many forces do you have acting on this box? Anyone? How many? In general? 3? Which one? Number 1? Normal, of course. There is support acting up. Normal force. What's number 2? Tension. Yeah, we see touching means a force. Force of tension. What's number 3? Someone said friction. Does friction act on this box in general? Yes. So in general, 4 forces might act on it. But again, before the first exam, we will neglect friction. And here, of course, we have 2 forces. This is what I like. Big M, little m. We could have used M1, M2 to differentiate between the masses, so we can use just different letters, big M, little m. Now, this is not the same force as that. Force of friction, well, force of friction is 0, we neglect it, and the force of tension number 1 is acting horizontally on the big box, and force of tension number 2 acting vertically on a small box. So those are not the same forces. They just can't be the same because direction is different. But we can say something very important about those forces. They have the same magnitude. Why? Well, because the string has no mass. In real life it has, but we neglect that. We only use massless connectors, massless strings, cables. And in that situation, if we would write as Newton's second law for a spring, like for a string, because it has no mass, and here we had forces acting on it, 0 times acceleration should be force number star plus force number hat, doesn't matter. So these 2 forces must have the same magnitude. So a string is a very convenient device which redirects the force. Yeah? The tension, force of tension was directed horizontally, and here it's directed vertically. However, magnitude of this force inside the string remains the same. That's a very important fact. So technically, we don't need to keep 2 values for the magnitudes. It's the same number. Well, now, just as an example, we can solve this particular problem. Again, neglect friction. When we neglect friction, only 3 forces left acting on the box on the top. Force of tension, normal force, force of gravity, 3 times 10, 30 newtons. This picture immediately tells us that force, normal force which supports the box, also should be equal to 30 newtons because gravity and normal should cancel each other out. But unfortunately, this picture doesn't help to calculate force of tension. The law, the Newton's second law, says that net force acting on this box has to be equal to the mass of this box times acceleration of this box, and relative to x-axis, that gives us tension should be equal to, well, 3, that's the mass, 3 times A. That's all we can write. This equation has 2 unknowns. However, lucky us, we have a second object connected to the first one. So we have to use that connection. This object has only 2 forces acting on it. And for this object, all forces are vertical. So for this object, x-axis doesn't play any role. And if you keep in mind that experiment, it tells you also how we should direct acceleration for each object, actually. For this guy, if we let it go, no friction, friction doesn't prevent it from sliding. It's going to be sliding to the right, faster and faster. So the object number 1 should have acceleration directed to the right. What about the object number 2? How does acceleration number 2 point? What do you say? Oh, okay, easier question. The object number 2 moves in a certain direction. How does velocity point? What is the direction of its velocity? What do you think? What? Someone from this area should tell me the direction of velocity of the smaller object is. That's not the direction. Negative is not a direction. Direction might be left, right, up, down, south, north. That's direction. Down, down. It travels down, so its velocity points down. Now, is it slowing up, speeding up, or slowing down? What do you think? Speeding up or slowing down on its way down? Well, you saw it. Initially, it was at rest, and then it was moving, so it's not at rest anymore. So what was happening to speed? Speeding up. If it's speeding up, means acceleration should have the same direction as velocity. Remember, we learned it, and now we use it again. So acceleration, bless you, should point down, which means the component of the acceleration relative to y-axis will be negative. Well, now, this is tension. This is little m times g. And we know this mass, 1. How do we know? We can read. It says right here. So how do we write the equation for this object? Well, technically, the starting equation looks exactly the same way. F net equals ma. Well, technically, a2. Yeah, it's a different acceleration. Now, F net now has 2 forces. Yeah. Tension, which points up, and gravity, which points down. and equal to 1 times 10 should be equal to mass, which is 1 kilogram, times. Do we know acceleration? No. But we know something about it. We know its direction. We know it has to be negative. So this is how we can explicitly demonstrate the fact that acceleration has a negative component. In this expression, this variable a represents the magnitude of acceleration, and magnitude times -1 gives the component. So we said before, because the string is massless, magnitude of tension remains the same, so this is the same number. In these equations, Ft represents the same number. What about acceleration? Technically, it's different because it points differently. But what about the magnitude of the acceleration? Same. Why? There is a reason for that. Very important reason. Because it's a string, not a spring. What is the difference between a string and a spring? Where is my spring? What can we do to a spring? Stretch it. Spring might change its length. Spring might change its length. String, unstretchable. So the string has a fixed length no matter what. And if, let's say, this box travels down by 1 centimeter, that means automatically this box travels to the right, but also by 1 centimeter. They travel same distance, same time. They must have the same speed. They must have the same magnitude for acceleration. So that letter A and this letter A represent the same number, magnitude of the acceleration. What we have now is, again, a case of two equations and two unknowns. We can just rewrite the equations. Number one, equation number one says tension equals 3 times A. Equation number 2 says tension minus 10 equals negative A. Physics is what? Done. Well, this is a simple equation, of course, to solve, and you should practice, and that's going to be the answer for that. And this example covers all situations when several objects, normally just two, connected and move simultaneously, maybe in different directions, doesn't matter. As long as we use massless, unstretchable string, we always can connect the motion of the object number one and the motion of the object number two. Any questions? Next example. So the question for you, time for me to prepare. Now use the book. My pen. So this is what is literally happening. There is a hand which is touching a big box, and the big box is touching a small box, and they move together in the same direction. That's it, nothing else. We neglect friction for now. Now, before we technically answer this question, we should answer a different question. What is a system? We use this word again and again and again, but what does it mean? What do you think? The system is an object here. Or else, which object in this situation? Green? Blue? What do you think? What is a system? You want to have as a system two blocks together. Absolutely reasonable approach. But why not only left? Or why not only right? What's wrong with that? Yes. They don't know that. They can't think. For objects in nature, systems don't exist. Nature has no systems. We choose something to be a system because that makes our thinking easier. And when we choose something to be a system, how can we choose it? Any way we like. So the answer, a system is anything we want it to be. We want it to be this, we make this a system. We want it to be that, we make that our system. That's what we are interested right here, right now, in, and we can make the whole system made of both boxes together. So in this situation, we can choose the big box as an individual system and consider forces acting on the box number 1 only. We can choose the small box as an individual system and forget about everything else, consider only forces acting on the box number 2. Or we can choose the whole combination as a system. And every time when we choose a system, for that system, we can write the Newton's second law. That's why it's important to choose as many systems as possible, because for each system, we can write the Newton's law. So the number of systems is equal to the number of laws we can write. The more equations we have, the more information we can extract. So in this situation, 3 systems, which means 3 laws. 1 Newton's law for the green box, 1 Newton's law for the blue box, 1 Newton's law for the combined system. Well, that's what we have to do right now, write those laws. So which do you want to do first? Green, blue, or combined? Green. Not the best choice, but okay. So what do we know about it? Well, technically we should start from gravity because it doesn't disappear and normal, but because everything is happening horizontally, velocity points to the right, acceleration points to the right, vertical forces just cancel each other out, they don't really matter. Now, there is, of course, applied force which points to the right, and the magnitude of this force equals 15 newtons. How do we know? We can see. Are we done? So, no friction. In general, I would have to add another arrow in opposite direction, but if there is no friction, there is no that arrow. Are we done with the forces? You say no. What's missing? Absolutely. Touching means interacting. That's the rule. We have to remember that rule. We see touching, there's interaction. Interaction means there's a force. And the force acting from the blue box on the green box points how? Left, exactly. We have to add that force. Now, do we know the magnitude of it? No. but it exists. That's it. We can write a subscript like blue, green, from blue on green. That's it. Now we can write the law. That's our acceleration. That's our positive x direction. The law is on the screen, but we just have to write it specifically for this system. 15 newtons points to the right. Now, the force acting from a blue box on a green box points to the left, which means it must have a negative component. We don't know the number for the magnitude of that force, so we have to use a letter, a label. And, well, we can write it like this. It has to be equal to negative magnitude of that force. So when I say it like that, I automatically assign that symbol FBG for the magnitude of a force acting from a blue box on a green box. And that has to be equal to 3 kilograms times acceleration. Well, acceleration of a green box, technically. And that's it. We cannot do anything else about this system. Well, and that equation has two unknowns. That is why this wasn't the best choice. Well, let's try another one. Never give up, right? So the blue box also travels to the right, acceleration, and theoretically there's a force of gravity acting on it and normal force acting on it. But again, they cancel each other out. Only horizontal vectors are important, and no friction here again. This is my hand touching this box. Look at this, because I'm going to ask you a question, very important question, very important, complicated, difficult question. Does my hand touch the blue box? Remember that. Because I can assure you, some of you would tell me in the future that the force acting on the blue box equals 15. Does my hand touch it? No. So this force just can't be 15, because 15 is a different force. 15 is a force acting on the green box. Do we know the magnitude of this force acting? No. So we just have to label it. This is the force acting from green on blue. That's what we know. But good thing about interaction is it obeys the Newton's third law. The force acting from green on blue must have the same magnitude as the force acting from blue on green. Newton's third law. That's a connection which we can use. Now we can write the law for this box. That unknown force and nothing else, so should be equal to mass times acceleration of this box. Now we have to say something about these accelerations. Say something about these two accelerations, please. You asking or telling? So tell it. They should be the same. Why? Because they move together. In this situation, they're not connected by a string, but they're connected by this interaction. So if this travels 1 centimeter every second, this travels 1 centimeter every second, they make the same displacement over same time, everything kinematically the same. So, which means we don't have to keep using those subscripts. Now again, we have two equations. We can solve those equations. Equation number 1, the equation number 2. But we didn't use yet the third possible system, composed of both together. What is the total mass of this system? How do we know? We can count, we can add 3 and 2. For this system, of course, in general, there is a force of gravity, there's a normal force, which again cancel each other out. There's a force applied from a hand. Now, do we have any other forces acting on it? No. No friction, nothing else to add. So for this situation, there's only one force acting, and it has to be equal to mass times acceleration, which is supposed to be, again, the same number. Turns out this is the most convenient choice of a system, because now we can immediately calculate the acceleration. 15 over 5, 3 meters per second squared. And if we know acceleration, we can calculate all other forces. Or we could do it differently. We could have solved the equations first, calculate force and acceleration, and then we could check that the third equation also works. We'll always have more equations than we need. Any questions? Well, so these are answers. Now, a very similar situations might happen in a real life. But situation on the top and situation on the bottom are different. What's the difference? Well, here at the top, the small car pushes on a big truck. So if I draw a free body diagram for the car, what should I draw? Gravity, naturally, normal. And the engine propels that car ahead, so applied force. And here we have interaction, so there is a force from the track on the car. And theoretically, there has to be some resistance. This is how many forces acting on a car. For the truck, what do we have? Again, gravity, normal, naturally some resistance, and there's a force which propels it, force acting from a car on the truck. That's it. So now we have only 4. Now there's a connection provided by the Newton's third law. The force acting from a car on a truck should be equal to the force acting, well, should have opposite direction, but same magnitude, the force acting from the truck on a car. This is the connection. What difference do we see at the bottom picture? Well, now the engine propels the truck. So now, if we draw a free body diagram for the truck, we should have same normal force, same force of gravity, some resistance, and the force acting from a car on a truck doesn't disappear. Touching means interacting. But now, the engine propels the truck ahead, so the applied force now should be acting on the truck. So totally we have 1, 2, 3, 4, 5 forces acting on it. But for the little car, well, naturally again, gravity, normal, some resistance, and the force acting on a car, like from a truck on a car. And that force, from our common sense experience, should point to the right, because that's how the truck makes it move to the right, which means I have to change my picture here. And that's the trickiest part of this analysis. But Newton's third law tells us that the force acting from a car on a truck and the force acting from a truck on a car should be opposite to each other. So if we know for sure the force acting from a truck on a car should point to the right, because that's the only reason it might travel to the right, they couple together, that means the force acting from a car on a truck should point to the left. Theoretically, if we even didn't make that conclusion, when we would be using the law, we would see which component is positive or negative automatically. Well, in this situation, let's just list the systems. We can choose as a system the green box. We can choose as a system, how do we call this color? For the box in the middle. Light blue, okay. We can choose as a system dark blue. 3. Are we done? No. We can choose as a system combination of first and second. We can choose as a system the combination of second and third. And finally, we can choose as a system the whole combination. And now, based on our previous experience, the first law, which we should write, should be written for the whole system. Because this law, Newton's second law, will automatically let us to calculate the acceleration of the whole system, of the whole 3 objects. And then when we know acceleration, we can draw a free body diagram for any individual box or for any combination of 2 boxes and calculate all forces which act between those boxes. We have a force of interaction between first and second box. We have the force of interaction between the second and third, and those forces will be different and not equal to 15, of course. And you're going to do this problem in your lab. And last example about tension. In this situation, everything is at rest. So there is a force of gravity acting on this weight. It's supposed to be equal to 30 times about 10, 300 newtons. But because it's at rest, the force of tension also should have the same magnitude, 300 newtons. But because it's an ideal, massless, not stretchable string, the same magnitude should be act inside this rope everywhere, which means here and here. 300 newtons here, 300 newtons here. But to compensate that force here, in the axle, what should be the magnitude of the force acting on this pulley equal to compensate 2 forces directed down? Someone should say the number. 600. This is a standard calculation for an object in equilibrium, 600 newtons. Well, thank you very much. I got it. All right.
Thank you.
I'm not sure when exactly.
I cannot hear you.